Hello? Hello? Okay, I guess we had some short technical issues. John Kowalski, who is our introducer, I think he's having a glitch. But I guess I just learned that you guys can hear me. So I apologize for this mishap. I guess we had some technical issues on our end. So, anyways, thank you for joining today. I'm up here in rainy Maryland, and I hope the weather is nicer wherever you are. So today we're going to talk about dispersing milling for battery and fuel cell applications. We are going to start out with a short introduction to just give you basically an overview of what we're trying to do at the business. And then we're going to go right into the dispersion and milling process overview. And from there, we're going to talk about different types of equipment and how that's being used, and what different accessories are available to really disperse and mill down these different types of slurries. And then we're going to round it off to talk a little bit about some lab capabilities that we offer. So with that, we'll go right into the company. So VMA Getzman is the manufacturer of these dispermats, these high-speed dispersers and media mills. The company was founded in 1972, so over 50 years ago, by this beautiful couple on the top there, Herman and Elke Getzmann. Herman they're both still alive. The company is now run by the two sons, Christian and Martin Getzmann. They are located in kind of dead center Germany. So if you are familiar with the map of Germany and some bigger cities like Cologne, they're about 30 miles east of Cologne in a very small town called Reichshof. So the family is still running the business, and BIC and VMA have had a strategic relationship going back all the way to 1988. So our former CEO at the BIC Additives was very impressed with the dispersion technology of VMA, and he brought some of these dispermats over to the United States, to Wallingford, and then to have them used in the lab. So when customers came in and did lab tours, they kind of saw these dispermats and they were wondering how they could buy those or where they could get them. And back then, VMA did not have representation here in the US or Canada. And so a deal was made so that we would become here at Big Gardner the exclusive distributor for the VMA Getzman dispermat. So that's how kind of that evolved. The company is about 100 employees worldwide, and they are known to make really high quality dissolvers, bead mills, as well as basket mills for lab space, pilot, and production facilities. And we started that pilot and production offering here in the United States about 5 years ago. And it's been a really successful endeavor for us. Okay, so go right in. So the material, it's used The machines are used to disperse different types of materials, especially lithium-ion applications. You have your silicon simple, silicon carbon composites, electrodes, oxides, lithium components, and for different types of applications. And we have had some also good successes in the fuel cell arena, specifically dispersing iridium oxide into different slurries. And then we would be using an APS air pressure system to mill down that material, which we will be talking a little bit later in more detail. Okay, so the company here is in the middle, so that's the new building, and that's where these machines are designed, and basically they're all over the place, um, all over the globe. So they're in about 100 different countries. And then we have a high-end dispersion lab here in the US, as well as at VMA in Germany. Okay, so the dispersion process is very simple. So we're basically trying to break up binding forces that hold particles together and reduce the particle size. So if you look at that picture, we start out with these larger clusters. They're called agglomerates, and we want to turn them back into the aggregate stage and ideally down to primary particle size. So that means we first start out with a dissolver where we are wetting our solid particles, and we mechanically break down these binding forces and reduce the particle size from the aggregate agglomerate level down to the aggregate level. And then we are actually going to mill the material to get down to the primary particle size. So in this slide here, you can see the kind of the layout more in pictures. So we start out with a dissolver disc, and where we are wetting these larger particle clusters. And then when we reached about 10 to 30 microns of particle size is when we actually use some sort of a media mill, either a basket mill or a horizontal mill or a bead mill type attachment. And then we basically break down these aggregates down to primary particle size, where then we need some type of additives to keep them in a suspended state. And our sister company, Big Additives, is very helpful with giving recommendations to our customers, and also has some very good solutions available that help us stabilize these particles. Okay, so here we have an example of a cathode slurry that we processed using a dissolver. And basically what you can see here is an AE unit with a torque measurement sensor. That particular model has the ability to track and measure viscosity in real time with the torque measurement sensor, resolution of 0.1 Newton meters, which can be translated to about 10 centipoise. So it's very, very precise when it measures that in real time. So we're adding our carbon black, our PVDF, and NMP in this case, and then we added the active material, and then we used the disper mat with the vacuum chamber. We pulled out all the air, and then we were able to actually disperse this material. And what you see right there is about a 2-liter container. And we're tracking all the data in real time, and we're able to not only measure our torque or viscosity, we are getting also a value for the amount of energy we are putting in, our tip speed, our RPMs, as well as the temperature as well. So we are always able to really measure and monitor the temperature of our slurry. And then we're able to process the data and use that for upscale if we want to go from laboratory scale to pilot as well as manufacturing. So this is very helpful, especially that this particular model right there, we're able to actually see the tip speed, which is the peripheral speed of our blade, on display, which is a very important value when we want to go and upscale from the lab all the way up to production. So here you can see how we are actually milling an active material. So this is now milling of the cathode, the carbon black, and we have a video that John is going to show of what that looks like.
Can you hear me this time?
Yes, now we can hear you.
Okay,
You're back, and
here's your video.
So maybe that's perfect. Yeah. So you can see the basket mill is running very quiet. You have the control panel right there showing us the speed, the amount of energy in watts we're putting in, the torque value, as well as our tip speed on top, 14.1, which is kind of at the higher end of our milling speed, where we're looking at 9 to 15 meters per second. And then we have temperature without the temperature sensor was not hooked up, but here you can see we are oscillating the basket mill inside of our vessel. And there is a pumping wheel that we have on the inside of our basket that actually is creating a vortex, and that's sucking our mill base, our active material, into our basket mill. And we have a very good circulation of our active material, of our slurry in and out of the basket. So this is a very effective way of going from the aggregate down to the primary particle size, and we were able to mill this material very efficiently, and then we were able to actually scale that up as well. So this is our TML basket mill that you saw here in that video. It's a simple attachment. You can see there is a clamping ring right below the motor. Where you see that VMA logo right below, there is a clamping ring. What we did was we removed the clamping ring and we replaced the dissolver shaft with the dissolver blade, and we put on this basket mill attachment. So basically, we were using one AE machine to do both our pre-dispersing as well as our milling with that basket mill attachment. So that's all it took to get from the agglomerates down to the aggregates with the dissolver disc. And then from the aggregate level to primary particle size, we were actually using the basket mill. So that particular basket mill also was fitted with a ceramic lined milling chamber and also a ceramic milling disc. The reason for that was we don't want any bleeding of stainless steel or metal into or carry that over into our slurry. So it's very important that when we mill these type of products, that we actually have also ceramic components inside of our mill to avoid any type of cross contamination. What we didn't do here, but what we also have available is milling under vacuum. So this is a standard TML basket mill, but we also offer a TML vacuum basket mill because some customers prefer to remove any type of air out of the slurry and then purge it with nitrogen or argon gas as an option. So this is also available, and that also yields very good milling results for this particular application. So here we LMIP cathode slurry. So here you can see that we're milling for about pre-dispersed for about 30 minutes. Our starting point was about 100 microns, pretty large. And then we milled down the material for about 30 minutes, also with the basket mill, and we were able to reduce the particle size to about 2 microns on average. So again, this is a high power microscope image that kind of shows you the particle size reduction and what we were able to do here in a relative quick time frame to go from 100 microns all the way down to 2 microns on average by pre-dispersing and then milling for a total of about 1 hour. So also looks really good. So going back to that TMS sensor, that's really helping customers to understand the change in viscosity during the dispersing and milling process. So on the standard machines, the torque is actually a calculated value by the frequency converter. So that actually measures the amount of energy we are putting in, and then it calculates that value. The calculation is not very precise, so there is some variance in that. So with the TMS sensor, we actually have an active sensor that is attached to the shaft, and that will measure and now calculate the torque value in real time to a resolution of 0.01 Newton meters. And I mentioned earlier that's about 10 centipoise of measurement. The values are displayed on the control panel, and it'll give us a really precise calculation of the viscosity change during our dispersion process. It's very repeatable and will give us excellent reproducibility from machine to machine. And basically, it's a measured value, not calculated. So it's really helpful from an R&D perspective, and especially if you want to go and upscale, that can also be very helpful for that as well. Okay, so the dispersion process, as I indicated, is always 2 steps. So we first pre-dispersing with the dissolver, our high-speed mixer, some of you call it. We are looking for a tip speed between 18 to 25 meters per second. Very important. Anything less than that is not going to give us the speed, the tip speed that we're looking for to properly deagglomerate our materials. That can also be done under vacuum. And then once we reach between 10 to 30 microns of particle size, is at that point when we can stop the pre-dispersion process, and then we start the fine dispersion or fine grinding or milling process with our vertical bead mills, basket mills, or horizontal bead mills. And that allows us to reduce the speed of our milling tool to about 10 to 16 meters per second. And that will give us really, really good milling results. That helps us produce particles somewhere in the low micron range. And if we use a nano kit on our vertical bead mill or horizontal bead mill, we're able to go below 100 nanometers of particle size. With the basket mill, we are somewhat limited. We can go down to about 500 nanometers when we use the nano kit and use the right media type. We're able to do that as well. Okay, what is really important, and that goes for any type of application, is when we start out with a dissolver that we actually use the correct diameter dispersion blade. And we always want to look at that we start out with about 1/3 the diameter to our vessel ratio diameter. So as you can see here on this slide on the right, we have a table, a graph that will give us different dispersion blade diameters for different vessel sizes. So if let's say I take a 1,000 liter vessel, I know I can use a 30 millimeter diameter blade as well as all the way up to a 70 millimeter, depending on my viscosity. So the sweet spot is somewhere around the 50 millimeter blade for that vessel size. And then depending on whether my viscosity is higher, then I would increase the blade diameter. If my viscosity is very low, I would go down in size. So if I have viscosity, let's say like 100 centipoise or lower, I would want to start probably out with a 30. And if I have anything in excess of like 10,000 centipoise or higher, I may want to go all the way up to a 70 millimeter blade to make sure that the product is actually moving inside my container and I can properly disperse the material. We also can scale that up, the same philosophy for scaling is also available for much larger containers, and we have also that data if you need it. Okay, here is a very important calculation that basically helps us get to our peripheral speed or tip speed of our blade. So what we do is we calculate the RPM, we multiply that by pi, and then we multiply that by the diameter of our dispersion blade. And if we want to calculate meters per second, we express the dispersion blade in meters. So let's say it's a 50 millimeter blade diameter, then we would express it as 0.05. And then we divide everything by 60. And that value is our actual tip speed, or circumferential speed of our blade. And we want to be anywhere between 18 to 25 meters per second for an optimum pre-dispersion tip speed. That's a very important calculation. You may want to write it down. We also, on all of our models going forward, with the new control panels, we will actually show you this value, and you don't have to calculate it anymore. So there'll be a window that'll have the actual tip speed calculated for you. The only thing you have to do is input the correct diameter, dispersion blade diameter that you will be using in the control panel, in that window, and then you'll be able to just look at it, and it'll give you automatically the calculated tip speed, which is very helpful, especially when you want to upscale. That's a very important value to look at. Okay. We also have a visual cue that will help us visually understand whether we are doing a good job pre-dispersing and we are optimizing everything. And it's called the donut effect. The donut effect is called that because it actually does look like a donut when we look inside of our container and we have the optimum tip speed. So you can see that is actually a perfect looking donut right there on our left. And you can see that the center of the blade is somewhat exposed, and the shearing, the breaking up of the binding forces is actually taking place around the edges of the blade where we have those teeth. And that's where you're actually shearing the material, and that's causing these van der Waals forces to break up and reducing those particles. So that's what you want to see. That's an optimum donut. So as you see on that slide right there, you see at the edge of the blade with the teeth is where the dispersing is happening, and that's where all the energy creates the shear force that the particles get broken up. So these pictures are, it's the same principle, but it's actually from a coatings formulation. But we felt the pictures make a lot of sense, and the same philosophy applies here. For this application, you can see the donut is well formed. We are putting in about 850 watts of energy, which is a good amount, and we are having an optimum tip speed of 21 meters per second. So I would look at this and say, hey, this looks really good. We are dispersing. We are definitely reducing particle size. We're going to have scenarios where we are not seeing the donut really like that, and where we have actually, let's say our viscosity is very low, and then the donut may not form. Doesn't mean you're not pre-dispersing. It just means that the donut would automatically collapse as soon as it's being formed, and that means you don't have the visual cue, but you just have to continue to disperse and then take a sample and read the sample and see where you are in terms of particle size reduction. But the optimum, the donut forms in viscosity ranges between 2,000 to 5,000 centipoise, somewhere in that range, and then you'll be able to actually see that donut. So important here for a good a pre-dispersion result is the time spent in our vessel, the donut effect, the tip speed, 18 to 25 meters per second, About the duration of the dispersion or pre-dispersion, what dispersion I would say, we're looking between 15 to 30 minutes on average. The blade diameter, the ratio to our vessel diameter, and then the right choice of impeller disc. So there are different types of designs out there. Some have more teeth, some have different teeth alignment, some have a different teeth design. So you want to just stick with one that works best for your application, and then you can scale up from there. The amount of mill base is important. We are looking or targeting at least a 50% fill rate in our container. We can go up all the way to 70% and as low as 40%. But the optimum is about 50%. That's what we want to aim for. Carbon black, zirconium, and filler concentration play a role, obviously, formulation related. We want to keep the temperature as low as possible. When we're dispersing, we are putting in energy automatically. So we're gonna see an increase in our temperature. So cooling becomes really important, especially when we are actually milling the active material. We definitely need to be able to cool our basket and or definitely our vessel and or the basket. So our very small basket mills like the TML05 don't have their separate cooling, but the container always needs to be cooled. And then if you go with larger mills, they all have cooling capabilities, so that becomes really important. And then obviously the additive package is really critical. That gives us better performance when we pre-disperse, keeping our particles in a suspended state so they don't flocculate back together. So that's also very important. And then when we reach the 10 to 30 microns particle size, and we want to get down to the primary particle size, is when we actually need to start the bead milling process. So in a bead mill, the shear forces are no longer created by that blade with the teeth. Now we actually have a rotor or a milling disc in a chamber, and that gets filled up with these beads, these called milling media, and they're helping us to produce the shear forces needed to continually break up these binding forces and reduce the particle size. So again, it's shear forces that are helping us achieve it. Sure, you have some grinding action by particles getting mauled in between the beads. We have a relatively high bead loading in our milling systems, so it's inevitable that there will be some material that gets crushed. But most of the particle size reduction is due to the shearing of the product and the breaking up of these binding forces that hold these aggregates together. So actually what's happening there, I always refer to that rubber duck example. As you maybe remember when you were a little kid in the bathtub and your mom gave you a rubber duck and you were trying to catch the rubber duck in the bathtub and you would clap your hands together, that rubber duck got pushed away, right? Through the fluid dynamics. So that kind of principle is actually what's happening inside of a bead mill. So as the beads collide and drift towards each other at very high speeds, the particles get actually pushed away. And that pushing motion, that shearing, is actually what's causing these particles to break up and separate. It's obvious that at some point you're going to have a particle that floats just in between, that gets pushed away by two colliding beads, and then another bead when it's drifting towards another pair of colliding beads, and then it gets crushed in the middle. So that obviously happens, but most of the shearing is really taking place or breaking up a particle size reduction is because we're breaking up these binding forces. So that's really what is happening inside of a bead mill. So that principle applies both to the horizontal bead mills as well as the vertical bead mill or basket mill. So that's the same idea of what's going on inside of a milling chamber. The critical factors there are, of course, the milling speed or the speed of our milling tool, 10 to 16 meters per second, or some people say 9 to 15. It's either or, but you want to be in that range. And you also want to make sure that you get high quality beads, preferably a zirconium oxide is what we are using, serum stabilized in the lab in Wallingford. A lot of our customers are using the same media and don't use glass or anything like that. You can see the specific weight is a lot lower when you're using glass compared to a zirconium oxide bead, and also the hardness. So the glass bead is a lot more brittle, break much easier than a zirconium bead. And you don't want to use glass also because you don't want the shards end up in your slurry. So the zirconium ceramic bead is a lot more friendly for this type of application. So they make many different types and sizes. So you want to make sure that you use the correct bead size depending on what particle size you're milling. So usually we start out with, when we go from a dissolver to the bead mill, we usually start out with a 1 to 1.2 millimeter bead, somewhere in that range. And then we work our way down by changing out the screen or dynamic gap. And then continue to decrease the bead size depending on what our particle size is, until we get super fine particles, and then we can go all the way down to, we have now beads that's not even on here that are 0.1 millimeter diameter. They are super, super fine, but we need them when we go into the very low nano range. We require those type of beads. And then obviously, the heavier the bead, the higher will be our kinetic energy. And that is also very important, especially when we break up these particles, binding forces, and it helps us speed up the process. Okay, so some critical parts that are important here in our bead milling process is obviously the particle size after the pre-dispersion with a high-speed mixer. So again, 10 to 30 microns of particle size. Then we want to look at the bead size. We start out again with about 1 to 1.2 millimeter, and then progressively work our way down. The specific weight of our beads, the higher the better, meaning we can put in more kinetic energy, which helps us with our process. The bead loading, it really depends on the milling system. So there are tables that explain exactly what the bead loading should be for each diameter of a milling disc and rotor disc diameter and milling chamber volume. So there is not one number that fits every system. So you really have to look at that depending on the manufacturer. Shape of the beads, very important. You want to always make sure that the beads are of good quality, that they are perfectly spherical and not overly used, where then you end up with we've seen beads that don't look like spheres anymore, they're more like footballs. And that's for not, when people don't replace them frequently. Depending on how often you use them, but don't replace them, or just use inferior bead qualities. We have encountered samples from customers that looked really good, or samples from suppliers that looked really good in the lab. And then when you place your first order and you look at these beads, they don't look that good anymore. So under the microscope, you can see that very clearly. Are they perfectly spherical, or are they kind of off-shaped? You don't want that. You want to pay a little bit more and then get a better quality bead. It's really, really important. Speed of the milling tool, again, 10 to 16 meters per second. Product temperature, very critical there. When we are milling, we're putting in a lot more energy than just with the dissolver disc. And there we really need to make sure that we manage that with the chiller. To that, I want to say that we have also in our lab good chilling systems. And the way you select a good quality chiller is there is good suppliers out there. We work, for example, with a company called Julabo. They make a very good product. But what's very important is that the motor power of the chiller matches the motor power of the dissolver or media mill. So if you're looking at, let's say, for the lab space, a 0.7 kilowatt or 75 kilowatt system, the disperser has 0.75 kilowatt motor power. Then you want to buy a chiller or get a chiller that matches that at a minimum. You can always oversize your chiller. There's nothing wrong with having more cooling power than needed, but you don't want to undersize your chiller because there's going to be a point when the chiller can no longer keep up with the energy that you're putting in and the heat generated because of that energy input. And then you're going to have a problem with rising temperatures, and that's not a good thing. You have to stop the mill, wait till it cools down, and then start up again. So always buy at least the amount of kilowatt power that the motor of the Dispermat has, and don't go below that. That's really, really important. The number of passes through the milling chamber or basket mill, so the milling time, total milling time. So there is really not a good number that I can give you. So we have seen, as you have seen in earlier slides, we have some applications we milled for 30 minutes and we got to 2 microns. And then we had applications where we're below 100 nanometers and we milled for an entire day. So it really depends how low you want to go, what type of slurry you're dealing with, what is that material like, what is our viscosity, and so on. So that all plays a role in our milling time. The average residence time of our product inside of the milling chamber. So how long is our product actually inside of the milling chamber? So I can obviously adjust the speed of our pump or of our milling disc or rotor, and that will dictate how long is that product actually going to stay in there. So that also plays a role. Again, viscosity of the mill base is very important. You want to have it thick enough that you're able to put in energy. If it's very thin, then it just kind of goes through. Means you need to mill a lot longer to get to the desired particle size. If the material is too thick, then you will have problem processing the slurry because it will not really go inside of your basket mill, pump through it, or in our horizontal mill, it could clog it up, and then you have a problem that you don't have any flow of your mill base in and out of the milling chamber. So you always want to make sure that you have at least a flowable product. Again, 2,000 to 5,000 centipoise is optimum. We can go high as long as it flows, but then you want to always keep an eye on that. That it's if it's thixotropic, for example, that could also be an issue, especially when you're using a basket mill because the material tends to settle out around the bars that are holding the basket in place. And if you don't have any movement there, then you're not milling that particular part of the mill base. So to remedy that, you can change the diameter of your dispersion blade that's on the bottom of our basket mill. And you'll see a picture here in a minute. That will then help you get the product agitated again, and that will move it if it's very thixotropic. So just to make sure that that is properly milled. You can see right here is our basket mill design. So you have a milling chamber. Inside of the milling chamber, you have your milling disc that is surrounded by the beads, the media, and then right above it, we have that pumping wheel that helps us suck our material back into the basket. And then right below on the bottom, we actually have a tight-fitted screen. Depending on the bead size, we have different mesh sizes. So, with a 1 to 1.2 millimeter bead, that's kind of like where we start out. We usually will recommend a 0.5 millimeter screen mesh, and that will ensure that the beads stay inside of the basket and don't come out of the basket mill. So that cowl split I mentioned on the bottom right there is actually drawing the mill base outside of the basket, and then it's pushing it back around to the top, where then that vortex will sucks it back in. So we have a very good flow and rotation of our mill base in and out of the basket. So that is very important, and that's what you're looking for. So let's say you have thixotropic material. It tends to settle out right around these bars that are holding the basket, right? And it's not moving. So that means if I'm increasing the diameter of my blade on the bottom, then I get more movement, more agitation, and that will help break that up. And then the vortex wheel does an excellent job sucking it back in to the basket for very good movement of the mill base inside, in and out of the basket. So this system, the TML, is really an excellent milling solution for a batch type operation in the lab as well as manufacturing. And it's very easy to work with, very easy to clean, and gives you excellent milling results all the way down to about 500 nanometers. So no problem there. It's really a very, very nice way of milling. Here you can see how the slurry gets sucked into the basket, and then right below on the picture, kind of see the layout of the mill with that pumping wheel on top, the milling disc, and then the screen separating the slurry and beads from the beads from the blade right below, and that will then basically spin at the same rate as our milling disc and draw out that slurry through the screen and then push it back on top. This is double walled. You can see the cooling channels right there. Very important that we are cooling that area. Our design is such that the basket mill is fully cooled all around on production scale as well, even on top. And that is very important because that's where you put in most of your energy. So I've seen and know that there are some mill manufacturers that actually have an open system right there where their screen is not on the bottom. It actually is right here where that cut is open and it's not closed. And that basically means two things: limited cooling, because when I have a screen there, I'm not able to cool properly. But that's where all my energy is. So I really want to cool that area. But a bigger problem is the wear on the screen, because this is exactly where I'm doing all my milling. So if I have a screen on the sidewall, that means all my beads are impacting the screen at a very high rate of speed. And that means also high wear of the screen, means bleeding of the material of the screen into my slurry. So if that's ceramic, you'll have also ceramic bleeding. If you have stainless steel, you'll end up with metal shavings inside or little deposits inside of your slurry. You don't want that. The bigger problem becomes when this has to be done out of ceramic. Ceramic is hard, but also brittle. And now you're going to have beads impacting a ceramic screen, tend to wear it down relatively quickly or break it, especially with handling when you're cleaning and so on, because of the brittle nature of the screen. So we much more prefer to have all that enclosed, have a ceramic liner on the inside, optimize the cooling potential of the mill that way, and then have just the ceramic screen on the bottom where it's not really affected by the impacting of the beads that much. So that is, in our opinion, a much more efficient way of milling down these active materials rather than have an ineffective mill design that is not really designed for battery or fuel cell applications, but rather more for coatings applications. So this is a huge advantage with that design of our mill. We have also an APS vertical bead mill, which is a simple attachment to our dissolver. Again, that's like with the quick change system, you're able to just buy that whole accessory as you see it on this picture, and that just replace the dissolver shaft with an APS system. So basically using one machine for both your pre-dispersing as well as your vertical milling. In this case, we basically have two vessels. We have a top container, and then we have a container on the bottom. So the top container, we see that a lot with the fuel cell application when they're milling that iridium oxide. So we have a relatively low viscosity of our mill base, and that's really good for this type of milling system. We can then fill our container about 50%, and we add, let's say we are using a 100 milliliter container. We have a fill rate of 50 milliliters of slurry of material, and then we are adding 50 milliliters of beads. So we have 100% bead loading or bead loading ratio, which is really good. Means we have a lot of milling action, especially if our viscosity is very low. There's a lot of milling going on, and we're able to effectively mill down the iridium very quickly with this system. So that is a batch system that you can see right there. We have the vessel on top that comes with the cover. The cover has an air socket installed, and then there is a drain plug on the bottom with the screen. During the milling, of course, the drain plug is inside of the vessel and ensuring that nothing runs out. And then when we are done milling, we remove the drain plug, we hook up an air hose to our socket or outlet or inlet, and then we are purging the vessel with air or an inert gas, and we can then push or purge out the material into a container that sits right below. That's our catch vessel that will then hold the milled material. Very effective. We can mill very quickly. The only downside to the APS is that it's not really scalable to extremely large volumes. So we can do that up to about 30 liters of material. If we want to go larger, then we really need to use a basket mill or a horizontal bead mill. But that is effective for up to about 30 liters of material. Iridium oxide also is extremely expensive, so a lot of customers are looking to not mill these huge quantities, and they are really okay with these smaller vessel sizes for that particular application. So again, big advantage, very fast milling, 100% loading of my beads. I can also fit it with ceramic milling chamber as well as ceramic milling discs on the inside. I have a shaft sealing system, so I completely seal it. I can also have a system where I can pull a vacuum, and then I can purge with nitrogen or argon, depending on the application. Different screens are available depending on the media size, so we can even go down to very fine media with this particular system and use just much smaller screen. For the standard laboratory scale, we can go to 7 liters, but for pilot we now develop, this is not on this presentation, up to 30 liters. So we actually need to update that, but that is something that we developed for one key customer, and we have very good results. But anything larger than that, for like hundreds of gallons or liters or thousands of liters, this is not really suitable because you wouldn't be able to really handle that large bead volume, and it would also get very, very expensive. Okay, then we also offer a host of horizontal mills. So we have the RS or the SL in our lab or for the lab space. So that really depends on the volume what you want to do. So we can get up to 1,000 liters per hour with the horizontal bead mill. And that is also something that can be really effective, especially if you want to go below 500 nanometers and you want to do large volume production. So that's something that you will need is more of a horizontal bead mill. We offer these in standard configurations. We offer that with ceramic. We offer that also with a nano kit that obviously is all fitted already in ceramic. And then we can do that screen, that super fine screen, 0.1 to 0.3 millimeter, giving us really the optimum low particle size that some customers need. So we see that very helpful for battery separator coating applications, where often they need to be, the particle size there needs to be below 100 nanometers and maybe smaller. So that's when you really need the nano mill layout to get down to that particle size. It's great. It's a great system. It's all enclosed. We have obviously the ability to do pass through or recirculation. That means I can actually set up multiple mills and then basically start out with one particle size and then basically run it in sequence and then circulate it that way to get to that desired particle size. Most likely, you're not going to be able to do it because you're going to need a lot of residence time in the milling chamber to really start breaking up these particles. So we can see that you need many cycles, especially for battery applications, to really break down the particle size, especially like the separator coatings, ceramic particles, they take a long time to break down. Okay. Then with just a couple slides here. So this is the new CV3 EVO. If you're looking for a lab scale model that gives you all these capabilities we talked about, basket milling with the vertical bead mill, the APS. So these are attachments that you can buy for this system. And it gives you all the tracking data as well as upscale data. So that's a really great machine, small footprint, perfect for the lab, and allows you to record the data. It comes also on the advanced model with the scale, so you're able to weigh out your materials right next to the dissolver and then convert it to a media mill as you need to use it during your application. We have the battery application dissolver with that integrated torque measurement system. So that's a turnkey solution. We also just are coming out with an updated version of that. So it has a facelift, but we also did one other thing. Now you can have this particular battery application dissolver with the option of buying a basket mill with the vacuum system also. So this is a vacuum, but you can also add now a vacuum basket mill onto the same machine, and you can do that change in less than 1 minute. And now you're using a pre-disperser under vacuum or nitrogen or any inert gas condition, and then you can do the same thing with doing the milling operation. So that's a really great development. We're very excited that we are offering that system now as a turnkey solution. Here you can see larger scale. So we also offer with the scraper system, variable container sizes, so we can all the way scale up from small laboratory all the way up to production. On the picture right here, you see actually a pilot unit, and then on the picture shows you also the wall scraper system to ensure that all the material is actually properly scraped off the container wall and then pushed in the center of our container, where then the blade takes over and pre-disperses all that material. What's really great about the C technology package that we have there is the ability to then record our data, store the data, attach it to a batch of name or number, and then recall that at a later time. And then we can actually scale that up all the way from lab to production by using these values. So we have a very tight upscale ratio, almost 1-to-1 from lab to manufacturing. So that's really helpful. And a lot of people really like that process control capability that they get with that machine. So early on, I spoke about that, that modularity, the ability to fit different attachments onto one dissolver. So that's kind of like the core philosophy behind VMA. And when Mr. Getzman founded VMA, he said, I want to have one machine that can be used for many different applications across the board. Lab space is scarce. We know that, you don't want to have 2-3 machines to do different things. We want you to be able to buy one machine and then accessorize it as you need it for your different processes or applications. So what you see right there is a dissolver. Can be used with the rotor stator or homogenizer, the SR, the vacuum system, a CDS, an APS, a vertical bead mill, a TML, which is the basketball we talked about, and a wall scraper system optionally available as well. And that basically rounds that out and gives you one machine that can do really everything that you needed to do in your lab or pilot as well as manufacturing. And that covers it for today. I hope this was helpful. And again, apologize for the glitch early on, but we got that covered.
Yeah, it's just me. You don't need to hear me, right? You're saying the important stuff, Andy.
Yeah, we can hear you. Thanks.
Yeah.
Welcome back, John.
Yeah, thanks. Good stuff as always. Sorry about the technical glitch. And we are running out of time too, but we did record this, and as soon as we close out, you'll shortly receive an automated link with that recording. Feel free to share it with colleagues, listen to it later this week or next week. If you do have any questions that do come up, you can simply hit reply to that, and it'll come to the marketing team here, and we'll route it to Andy, his team, or one of the other technical specialists we have on the team here. Let's see. Andy, any final thoughts? I love the modularity of the units.
I would say, John, everybody loves the modularity, but I think in closing, what I didn't mention, but everybody should be aware of, we have a really nice lab in Wallingford, Connecticut. That's a big USA. They are experts. You may already work with them. Erin Kelly is my partner up there. She's really knowledgeable with batteries and fuel cell applications. They have very good additives that work in these formulations. And we have a laboratory up there that's only for dispersion applications. We have a lot of that equipment that we talked about. And we would welcome for you to sign up and come up there and then run a trial with your material and show you how these different attachments actually work and the results that you would be getting. And then we can help you scale that up. It's a good way of, quantifying the different milling systems that are out there, learning something new and helping you maybe to make purchasing decisions down the road if you are interested in buying new equipment for the lab space, pilot, or even manufacturing. So that's a good starting point. We'd welcome to have you. We just need a few weeks to set that up if you are interested, and then we wouldn't charge you for the time in the lab. We would have you gladly there for a day or two to run this material at no charge with you on site to take part in the trial. We'll have a chemist supporting us, and then we can evaluate the results together and make a good decision on what works and what doesn't work. So hopefully we hear from you, and we can welcome you up to our lab.
All right. Thanks, Andy. Thanks, everyone, for joining us, and we look forward to seeing you on future webinars. Have a great rest of your day.
Thank you, everybody. See you.